In this video, I'm going to explain the concept of the net change theorem, which actually normally we just call it NCT. Well, basically, this net change theorem is just kind of expansion from what we saw previously on the second on the fundamental calculus theorem. It starts actually from the very first idea, which was that we have a function f of x, and this is equal to the derivative of the function big f of x. Now this big f of x get us in return the area between the function f of x and the x-axis for an interval. And this expression led us to something, this kind of diagram that we had, that we can move along from this f of x and this big f of x and this f prime of x by using derivatives and antiderivatives. As you can see, if you take the derivative of big f of x, you will get back to the f of x. Now, if you take a derivative of f of x, you will get back to the f prime of x. It will be like this: dy dx. And if you do the opposite, if you move from the f prime of x to the f of x, you need to do an antiderivative. From here to here, you will do this little snake, the antiderivative, and you move from the f of x to the big f of x, you will as well do this antiderivative. Now, this led us as well to something other idea, just to calculate the area between a function and the x-axis. We use this idea of the definite integral, which was the integral between b and a for f of x dx, and this was basically big f of x equal big f of b minus big f of a. Now, basically, this net change theorem stands. It's a conclusion that we can get starting from this. As we can just assume, say this is true, we could say as well that the integral between b and a of f prime of x dx, this would be equal to f of b minus f of a. Now this may not sound that interesting at all, but it actually has several applications on real life and many things. I'm just going to start out by something very simple, a very simple example, which actually it comes from physics. As you may have seen previously, it's you start with a function of position, which I'm going to call s of t. You can get to the function of velocity, which I will call v of t. So v of t, there it is. And you can move from velocity, from position to velocity, by taking its derivative with respect to time. And if you're in velocity function, you can move from this function to the acceleration function just by taking again its derivative, differential of velocity over the differential of time, its derivative, and you will get to the function actually that describes its acceleration. Now, expanding out this idea of the fundamental calculus theorem, we can use it backwards. So we can use it to move from the acceleration to velocity by taking its antiderivative, or the little snake. And we can move from velocity to position just by taking again its antiderivative. So I'm going to use this idea to expand this out for a very particular case, which is something actually very simple. Let's start with something very simple. Suppose we have a function, we have a particle which is moving along. It's moving along. I'm going to draw here this axis and this other axis. And this particle, it's moving with a constant velocity, which I'm going to say there it is. This particle is moving with a constant velocity of 3 meters per second. And we want to know, this axis, of course, will be time, and this axis will be velocity with respect to time. We want to know for this particle with a constant velocity, what would be its net change in position, or what would be change of position with this constant velocity. So in mathematics, we will write it down as this. Will be the integral from velocity for, I'm going to say, we want to know its change of position between the second 0 seconds and 3 seconds. And we're going to integrate its function of velocity with respect to time. And let's say this would look like this. Would be the integral between 3 and 0. For, in this case, it would be 3 meters per second, differential of time. Now, these 3 meters per second, it may look kind of weird, but it's actually something very similar to this. If we have a function, we want to integrate a function for an interval of b to a. This function is just a constant k, differential of x. The integral for this function will look like this. Will be k integral between a and b for x raised to the 0 dx. Now we know what this will look like. Will be k times x between this very ugly bar. There it is, between b and a. So at the end, this will look like this. Will be k times b minus k times a. So we can apply this to what we have here. We want to know the net change in position for this particle, which is moving with a constant velocity of 3 meters per second. This will look like this. Will be the integral of the result of this will be 3. I'm going to write like this: 3 meters per second times time, because we have here this differential of time, so our variable is time. It will look like this integral, and the interval will be between 3 and 0. Now let's see. So if we apply this out, it will look like this. Will be 3 meters per second will be times this. We have to evaluate it on 3 seconds. Will be 3 seconds will be minus the other one. It will be 3 meters per second times 0 seconds. We can see the second term will cancel out because we have multiplication times 0. And now this on the first term, we have this seconds will be over 1, so we can cancel out these seconds and seconds, and we see the result of this after all will be 9 meters. Now if we look this on the graph over here, we can literally count the area below the function. You can see I'm going to do my best to draw this out here. This is as we can see, the area below this function is literally 9 units, which is 1, 2, 3, 4, 5, 6, 7, 8, 9 units. Now this in mathematics would be like 9 units squared, but we have a context here. These units represent, these 9 meters represents how many meters this particle moved away from between the second 0 and the third second with this constant velocity. And that's what basically represents this idea of the net change theorem. We take the derivative of a function and we get in return the net change for the original function. This sounds kind of silly with this expression alone just by itself, but believe me, this is very useful in many ways in real life. So let's move to another example now and let's see how to use it.